To continue on with the process of the difference between the two different types of smooth muscle, phasic and tonic, this one we've been talking about here is phasic smooth muscle, which is happening in brief bursts. As we said, it's able to contract and relax as long as that phosphate is still connected from the MLCK. But as soon as MLCP comes along, it removes that additional phosphate and completely disables the ability of myosin to connect to actin. But something interesting happens when there's a high influx of calcium from extracellular places through different factors. It disables Rho kinase in a high amount, which then allows a high amount of MLCP to be within the cell. When you have that high amount of MLCP, it actually removes that phosphate a little bit earlier on. And when that phosphate is removed in this stage, so the MLCP would come along here, it would remove this phosphate, causing it to stay. So if we're looking up here, this is actually where it happens. So that's the MLCP. It comes along, removes the phosphate. As it's losing the other phosphate in ADP, it stays connected and changes conformationally, and now it's kind of stuck in the uncocked position to the actin. And that allows it to stay in that position for a really long time, contracted without the use of energy. And that's more exemplary of tonic smooth muscle. And it eventually does disconnect. There's this thing called the latch state. It takes a long time for that ATP to come along and actually bind and release the myosin from the actin. And so that's the major difference between actin and of the two types of smooth muscle, phasic and tonic. Here are the cycles that we just went over, all kind of compared next to each other. We have skeletal muscle, phasic muscle, and tonic muscle. And so moving on to what are the major differences between the two. For skeletal muscle and smooth muscle, there's a big difference in control. Skeletal muscle, you're able to voluntarily, through the somatic nervous system, control, while smooth muscle is involuntary or controlled by the autonomic nervous system through the PNS and SNS. Within skeletal muscle, it's multinucleated, while smooth muscle has a single central nucleus. Smooth muscle is a lot slower than skeletal muscle with its contractions. The skeletal muscle receives most of its calcium from the sarcoplasmic reticulum, while the smooth muscle gets help, depending on the case. Like we said, with phasic, it gets a lot of its calcium from the sarcoplasmic reticulum as well, but with tonic, it gets a lot of it from extracellular. And so another big difference is the mechanism here. There isn't a binding that removes the tropomyosin, but there's a binding that changes the shape of your myosin that then allows it to move the tropomyosin itself from the actin site. So the binding mechanism is a little bit different as well. Another big difference is fatigue. So with skeletal muscle, it has pretty high fatigue when it comes to the comparison versus smooth muscle. Smooth muscle can contract for very long periods of time. Alright, now focusing a little bit more on muscle sensory receptors and reflexes. You have a couple different neurons that innervate into the muscle that have different uses. So this is muscle here. Towards the tendon we have a GTO, or a Golgi tendon organ. And here we have the alpha efferent motor neurons. And these ones are the more common ones. These ones are the ones that allow us to directly contract. But then we have the muscle spindle fibers, or neurons that affect afferent sensory. So GTOs and muscle spindle fibers are what we're going to focus on, and they both are afferent sensory neurons. And from this, for muscle fibers, these are muscle spindles is what we're focusing on here, and those are located within the muscle fibers, and these detect changes in muscle strength and changes in length within length. And these are composed of these little guys here, intrafusal fibers, that are innervated by 1A and 2A afferents, which also detect different things. 1A is more of the motion of the muscle, while 2 is like stretched and in a locked position. And so these different fibers here initiate the stretch reflex, so when the muscle is stretched, the spindle fiber triggers and contracts the muscle to resist the stretch. And so this isn't through our receptors that go back to our brain, but it's done afferently. As far as Golgi afferent sensory, Golgi tendon organs, they're located on the tendons, and these ones detect muscle tension and force during contraction. And compared to intrafusal, that are 1A and 2, Golgi tendon organs are innervated by 1B afferent fibers. And so when this excessive force is detected from muscle tension being contracted, the GTOs trigger an inhibition which relaxes the muscle to prevent damage. There was a really cool demonstration in class where we could overcome that contraction. So when you stretch, you hit a point and your GTOs are like, heck no, we're not gonna let you keep going. But if you activate really hard with those alpha efferent motor neurons, you have your protagonist muscle, which is contracting, your antagonist muscle, which is relaxing. So as you contract really hard with your protagonist, the antagonist will relax, and which overrides your Golgi tendon organ that is preventing the overstretching of that muscle. A couple reflexes I'd like to discuss here are the stretch reflex, which is a monosynaptic reflex, and it's stimulated by muscle stretching. It directly synapses on your alpha motor neuron, and a good example of this is your knee jerk reflex, where you get your knee tapped and your leg kicks up. So these are a couple steps here. So you go through a muscle spindle senses a stretch when you get tapped on the knee. The sensory motor neuron conducts an action potential, which then leads to the synapse with the alpha motor neuron and interneuron. And so it stimulates the quad, but then inhibits the hamstring, so it contracts the quad, and then the hamstring relaxes, causing you to kick forward. We then have this final reflex I'd like to talk about, the withdrawal reflex, or the flexor reflex, which is a polysynaptic reflex and is stimulated through a painful stimulus, like touching a hot stove, or getting poked by something, or having something like tossed at you. It's going to cause you to withdraw. And so with this withdrawal reflex, it's a reflex that doesn't make it back to your central nervous system. It actually just goes right to your spinal cord. It synapses and returns an action that allows you to withdraw, and it's hardwired right into your body. So the steps here would start off with that stimulus detection, like a pin poking you, and that then leads to which would activate your nociceptor, which is a pain receptor in the skin, which detects that harmful stimulus, like a pin or the hot stove or something, some high pressure. This affects that afferent or sensory neuron that leads back in synapses. So in this example, this one goes up to the brain, but it would lead back in synapse. It would cut this connection off. This wouldn't happen here. And it would go directly synapsing in your spinal cord. And then when it enters in this dorsal horn, and when it synapses with that interneuron, it then does a little interneuron processing and excites these interneurons to stimulate alpha motor neurons to contract flexor muscles, like you're contracting your bicep and pulling it away, or contracting your hamstring to bend your knee from pulling away. And so these inhibitory interneurons would then also, you'd have the excitatory ones and you'd have inhibitory ones, which suppress activity with extensor muscles. And so you'd only have that high reflex of flexor muscles. And this would then cause that motor response out of the ventral horn, cause that withdrawal movement. And so a good example of this would then be like if you step on a sharp tack, your pain receptors in your foot activate, sensory neurons carry the pain signal to the spinal cord, interneurons activate, and activate the motor neurons, which then flex the hip and the knee, causing your leg to pull away and away from the stimulus. And I believe that is it. Thanks.